Just to jog our memory, we've been looking at the impulse equation. What's the impulse equation? First of all, the first concept I gave you in lesson 1 was just what momentum was. What was our abbrev for momentum? We couldn't use m because that was taken by mass. Yet we said, first of all, momentum was the amount of motion an object has, and its mass times velocity. That's the first equation. The one next to it on your green sheet, that's the impulse equation, where I said, and I may have the order wrong, but I know I would have given you something like there would have been a delta P, there would have been an F delta T, and there would have been an M delta V. It's a 3-in-1 equation. I might have written it in a different order on your green sheet. But delta P, what's delta an abbrev for? What's change in anything? So the first way that I can find the change in momentum is if I happen to know the final momentum, and if I happen to know the initial momentum, just subtract them. Pay attention to directions, though. If they're in opposite directions, you have to let one be positive and one be. Ryan, that's your cue. One be. Okay, you back with me? You look like you were zoning out, so that's why I did the point there. Or if you ask, what's another word for change in momentum? Starts with letter I. Okay, they're interchangeable, impulse, change of momentum. Or if they ask me to find the impulse and they give me a force and a time, I can do that. Or if I know the final and initial velocity, I can do that. But Amber, what I really said to you on Friday, where the impulse equation shined, was if I do that, because this was an equation that contained F equals ma and VF equals VI plus AT kind of in disguise, it allowed us to save some time. It allowed us to save some writing. But this is important. Pretty much for all of this, you might recall I kept saying to you something like, you can solve this with F equals MA and VF equals VI plus AT. And that's my way of saying, Jazz and Deep, don't leave stuff blank. If you can't solve it with the impulse equation, but you think you could solve it by going VF equals VI plus AT, find A, and F equals what, MA, then please do that. Okay? You brought the snack out. They're all good now. We're back to paying attention here. Okay? All right. So, let's look at example 8. It says, consider the diagram at the right for the next 3 questions. The diagram depicts initial and final velocities of an 800-kilogram car in 2 different collisions with the wall. Here's what I notice. In case A, there is a change in direction. See it? We're going to have to let Ryan one way be positive and one way be. This is your line. Okay? What do you want to let be positive, the 5 or the 4? Pick. Okay? I'm going to disagree with you, and I'm going to show you why for a clever reason. By the way, it's not wrong to let to the right always be positive and to the left always be negative. But for impulse, I often let final be positive and initial be negative, and I'll show you the clever reason why. So do me a favor. Put a negative in front of the 5, a positive in front of the 4, a negative in front of this 5, and a positive in front of the 0. Tell you, I know positive 0 is still 0, but this is my way of saying I noticed and looked for a change in direction. Okay? It says this. In case A, the car rebounds upon collision. In case B, the car hits the wall, crumples, and stops. Let's assume that the collision time for each one is the same. Part I asks, which one does the car experience the greatest momentum change? And our options are case A, case B. No, they're both the same. Or I need more information. You know what? We haven't voted for a while. Let's vote. How high you hold your hand up is how sure you are of the answer. So in which case does the car experience the greatest momentum change? Who says, Mr. Dewick, I think case A has the biggest momentum change. Case A, I got 1, 2, 3, I got 4, I got 5, I got 6, I got 6. Weird. No, case B, because it comes to a stop. 1, 2, 3, 4, 5, 6, 7. And then Sean did this. Is that a vote, Sean, or is it? Nope. Okay. Both the same. Is that a vote? Need more information. Some of you didn't vote, and I'd call you on it, but I want to get to the proof instead. We got a nearly 50-50 split here. This morning was interesting. Everyone but one. So different classes, different opinions. How can I figure this out? How can I figure out the change in momentum? Let's see if we can make a little proof right here. So it wants us to find the change in momentum. Look at your impulse equation on your green sheet. Which version of the impulse equation, of the change in momentum equation, would I use for this specific situation? Yeah. Oh, sorry? Yeah, I'm going to go mv final minus mv initial. If they had given me a force and a time, I'd use that one, but don't have that. Okay. David, keep going. What's the mass? Oh, now I need to divide this into situations. I'm going to use this for both of these. Now I'm going to change colors just so you can see. I'm going to go case A and case B. Fair enough? What's the mass? The question does tell you if you go hunting for it. Good. What's V final in case A? Good. Minus, what's the mass? 800. What's V initial? No, it's not.
Oh, -5.
And Matt, this is why I said to you, sometimes it's easier to let the initial be negative. Can you see I have a minus, which is a... I've just learned I make less dumb mistakes if everything's positive. I will not take marks off Kenta if you let initial be positive and final be negative. Totally fine. I've just picked up the habit over the years of saying, oh, I'll get a minus, which is a plus, which is a plus, no pun intended. David, what'd you get? You went to your calculator by now and typed it in without me having to tell you, right? 7,200? Kilogram meters per second, or you could say Newton seconds. What about in the second situation? Well, what's V final? So it's going to be 800 times 0 minus, and then 800 times -5. I can do this one in my head. What's a minus? The same as a plus. I think you get... Is that right? Which one underwent a bigger change in momentum? Why? Why should you have been able to look at this diagram and know for a fact that it was case A?
Because momentum changed to a negative value.
Let's not talk about momentum. Talk to me about velocity. What's the velocity change of case A? 9. Negative or positive, I don't care. But a total, do you see it, Amber, of 9. We were going 5 in one direction, 4 in the other direction. That's a change of 9. What's the velocity change in part B? 5. I would have said that's a much bigger change in velocity in part A. It's going to have a bigger change in momentum. Number 2, in which case does the car experience the greatest impulse? Peter. I'll give you a hint. It's a trick question. Why? Yes! Thank you, Peter. I knew I could count on you. I didn't think you would get that at all. I am so impressed. Peter, I had confidence. I knew I could count on you. Well done. This is just me asking, have you clued in that impulse and change in momentum are the same? Whew. Even Peter got that. Yes. Sorry. Oh. The impulse encountered by the 800 kilogram car in case A has a magnitude of, what did you say? 7,200. And you could say kilogram meters per, circle it, sorry, 7,200. You could say kilogram meters per second or Newton seconds. Okay? So, based on what you just saw, let's see if we can make a prediction about car crashes. Turn the page. Or next page over. Is that what it is? Which type of collision is worse for a passenger? Let's assume the initial velocities and the time of impact and the masses are the same in each collision. What's worse? A head-on collision where the two cars stick together? Or a head-on collision where the two cars bounce apart? And convince me. What's worse?
I think the ones with the car pretty
Why?
Because the velocity change is pretty good.
Ah, looking at the previous picture. Okay, so I agree it's going to have a bigger that. So what does that affect? What does that make larger? Okay. How does that mean more damage to a person? What's another way to calculate impulse that involves a force? What's the other version of
Force delta.
Okay, so we got a bigger impulse, but I told you the time of impact was the same. So what had to get bigger to get the same impulse if I didn't let time to get a bigger impulse if I didn't let time get bigger? What got larger? Okay. This is the domino chain we're doing here. I know there had to be a bigger change in velocity, and since Amber, impulse is mass times change in velocity, bigger impulse. But another way to think about impulse is force times time. Oh, same time, you say? Bigger force. And then F equals what? What got bigger, the mass or the acceleration? And what does damage? Okay, this is why bouncing off something is worse, because you end up with bigger A. Or if you watch football or hockey, the biggest collisions between the athletes are not when they smash into each other and come to a stop. The biggest tackles, tackles in football are where the person runs through the ball carrier and sends them backwards. That's when you're kind of go, oh! Or the biggest body checks in hockey are where they both bounce off of each other in opposite directions. That's when you go, ooh, I think that hurt even more. Yes, because there was a bigger change in velocity, bigger impulse. Okay? Is that all right? How can we make it more likely that cars will stick together and not bounce off of each other? Let's come back to that. Example 10 then. The diagram below depicts the changes in velocity of a ball. Look at the picture. Is there a change in direction? We better let Ryan one way be and one way be. Okay. What do you want to let be positive? Clever trick. Let final be positive and initial be negative. Then you'll get a minus, which is a. Okay. You don't have to do that if you don't want to, but I'm going to. So I'm going to go like this. Positive, negative. Positive, negative. To someone who does not have a physics background, Jazz, they might say, oh, this has a change in velocity of 5. This has a change in velocity of 2. Is that correct? All right. Which one has the biggest delta V? Well, you know what? What is the delta V of case A? 5 minus 10, 15. Meters per second, not kilogram meters per second. I didn't multiply it by mass, but 15. What is the delta V of situation B? Okay. Well, be obvious. Which one had a bigger change in velocity? Case A or case B? Case B, explanation, see below. Which one do you think then underwent the biggest acceleration? Case A or case B? Kritesh. Why? You're right. You know what? I don't know if you remember, at the very beginning of the kinematics unit, I defined acceleration as delta V over T. So which one's going to have the bigger acceleration? The one with the bigger change in velocity, which is B. Yep. Okay. Which one's going to have a bigger change in momentum then? Derek. Why? I would even go like this. It's M delta V. Bigger delta V, same M. So bigger change in momentum. Which one's going to have a bigger force times time? Why? Same thing. This is another way to calculate impulse. Same as that. Force times time, or m delta v. We're just starting to look at the physics of collisions. But basically, in any collision, especially if we're talking about car crashes, if I can make the delta t get bigger, I can make the force get smaller. How can we make collisions last longer? Even before, you could say no engine. Yes and no. We need engines for most of our cars unless they're electric. But one of the advantages electric cars have is more room to do. They're called something zones. Crumple zones, which no engine would be a crumple zone. But we built crumple zones into cars. And that's really been the last 30 or 40 years of car safety. The initial cars from the 1950s and 60s had no crumple zones. They were designed to be hit and remain immaculate. But that meant that the passengers had massive accelerations. What's your homework? This is going to seem like a lot. I'm not going to finish the lesson tomorrow, so you're going to get some time tomorrow as well. On this first page, every question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But before you turn the page, I changed the order of the questions and I forgot to change the order of the answers. So do me a favor. Circle that first 20, draw an arrow. It should go in front of the next time you see a 20 meters per second. It should go there. Sorry. Student caught that this morning. Okay. Then what else did I assign this morning, Mr. Dewick? I can't remember. We're going to skip some. I'm going to give you some practice. So I said do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, but you can skip 16. So cross out 16. 17, 18, and 19. Put a star next to number 20. This is a question that's probably tougher than I would ask, but see if you can have the aha moment and figure it out yourself. And I crossed out Calvin and Hobbes, but you can try number 22. You can cross out 23 if you want. You can try it if you're a nerd, but you don't need to do it. Put your pencils down, look up. This is a pretty good explanation. This was made by a couple of kids from Britain as a class project. It's cute. It's a little animation. I thought it was very cute. But the physics is also very, very good. See if we can figure this out ourselves.
Hello and welcome to today's lecture from Brick University. Hi, I'm Nick.
And I'm Jane.
Today we're going to look at momentum and how we can use this to understand why we need crumple zones in our cars. Let's start off by looking at some theory on the whiteboard.
So let's walk to the whiteboard of science.
Let's remind ourselves that momentum is equal to mass times velocity.
Is that correct? How would we write that? What's our abbrev for momentum? Okay, and the reason I keep harping that is I've had a couple of kids in a panic think that M is momentum. And so when I've said find momentum, they've said, oh, it's P divided by V, which doesn't help much. So you need to keep straight that P is momentum, not mass. Okay.
If our car weighs 1,000 kilograms and it is travelling at 25 meters per second, what is its momentum?
Without a calculator in your head. Okay, 25 units. Okay, 25,000 kilogram meters per second or Newton seconds. Okay.
That's right, you've got it. 25,000 kilograms meters per second. What happens when a car hits a wall? Because the car's velocity becomes zero, its momentum must change to zero during the collision. We can use the change of momentum formula to allow us to find the force that acts on the driver during the collision.
So we would write that, what's our brief for change in momentum? Delta P equals F times T. That's one of the versions in the 3-in-1 equation I gave you. Yes? So far I agree with all this. Right, Sean?
Rearranging the formula, we get force is equal to change of momentum divided by the time over which the collision acts.
Delta P over T. I think I told you the other day, that's actually what Isaac Newton published as his second law, not F equals ma. He was much more interested in impulse.
Now we can use this formula to see how we can reduce the force on the driver. Because the change of momentum will be the same for any specific collision, if we increase the time, it will make the force smaller. Now we can put this theory into practice by looking at crumple zones in a real collision. Let's go over to our brave stunt driver, Ollie. Ollie, are you ready to go?
I think so.
So, watch the little stunt driver in the car. Here's situation number 1 with the crumple zone. Okay. Now watch the stunt driver without a crumple zone. What did he do? Something else had to apply a force to bring him to a stop into the windshield, or even you might have a massive yank on the seatbelt, break your ribs potentially. So,
oh dear, I hope Ollie was okay after that second crash. Now let's go back to the whiteboard to see if we can work out the forces involved in those two collisions. What? So the car had a mass of 500 kilograms and a velocity of 10 meters per second. In the first collision, when the car had a crumple zone, the car and the wall were in contact for 1 second. So if we put those numbers into the formula, we can see we get a force of 5,000 newtons. Now let's look at the second collision. In this one, the car had no crumple zone. So the car had the same change of momentum, because it was still 500 kilograms, going at a velocity of 10 meters per second, but the contact time between the wall and the car was only 0.2 seconds. So if we put these numbers into the formula, this time we get a force that's much greater of 25,000 newtons, which is why poor old Ollie ended up being thrown out of his seat. You'll be pleased to know that Ollie has made a full recovery and will be ready to do some more experiments for us next week. That's all for this edition, so it's goodbye from me.
And goodbye from me.
pretty good explanation, especially if you weren't on your phone. Especially if you weren't on your phone. Were you on your phone? Looked like you were. I apologize. Sorry, YouTube. I'm accusing a student of being on their phone. We'll pause now.